Okay, hey everyone, I'm Alex Hanna. I'm a data scientist and hydrogeologist at Pacific Northwest National Laboratory, and lately I've been helping to develop a software product called Dream. So Dream is a software tool that allows you to design an optimal monitoring network at sites where there's some potential leakage going on in the subsurface. And so if you have a set of simulated leaks for your site, and they can be in a variety of formats, um, we take those simulated output files and construct an optimal monitoring network so that you have a way of quantifying the risks so that regulators and stakeholders and commercial partners and the general public are all on board with whatever it is that you'd like to do in the subsurface. And so Dream version 2 was released recently and it can be accessed at this URL. And there's example data sets and documentation there. And it can use outputs from several different reservoir simulators, including STOMP and NEFT, or really anything that outputs or converts to an HDF5 file. We should be able to make work without much trouble. It can also use leak simulations from reduced order models, like NRAP OpenIAM, which we just heard about from Veronica and Mark. And so Dream version 2 optimizes for the placement of point sensors, such as pressure or temperature or CO2 concentration or salinity, things like that we measure at a discrete point over some period of time. And then it also uses simulated annealing as its optimization algorithm, which works pretty well for the cases that we've tested it on, but it might struggle with larger and more complex field sites. And so we're currently developing a new version of Dream, which allows a bit more flexibility in the type of monitoring technologies that it considers using. So it allows for geophysical surveys that happen on a particular day or maybe recurring every 6 months to 2 years, something, and that might happen over some particular transect of the field or some area, rather than having a sensor installed in a wellbore and continuously monitoring a single discrete point in the subsurface. We're also working on including cross-bore geophysics, so anything where we're sending a signal from one wellbore to another and detecting the leaks happening everywhere in between. And so for the new version, we're also adding the ability to choose from a variety of different optimization algorithms so that you can try a few and see which algorithms produce the best results for your site. So MCMC, or simulated annealing, is kind of the default, and so it starts with a random monitoring plan and iteratively makes a series of small random changes to it until it develops an optimal monitoring plan. And that can be quick and efficient if it's appropriate to the complexity of the field site that you're monitoring. But if you have the time to be more thorough, you can also use a method like Monte Carlo, where you just try a huge number of random monitoring plans and choose the best one. Or you could do something even more exhaustive like grid search, where you essentially try every permutation of the monitoring techniques available and you choose the best one. So those approaches are a lot more likely to work, but they aren't always computationally feasible for a big complex site. So we're working on some other more sophisticated algorithms. So here's a simple example where there are two possible contaminant leaks, these two stars, and then this blue dot here represents our initial random monitoring well location. And then in this graph, you can see what the time to detection would be for leak 1 compared to leak 2 for that monitoring location. So that means we have two objectives. Ideally, we'd like both of those numbers to be as low as possible and be down here near the origin. So of course, in this pretty simple case, we can just see what the best places to monitor would be, right? It would be somewhere between these 2 points. But we can start with a pretty poor well placement and still find a good solution. And so we make a series of random changes to the well location, and it throws out any changes anytime they lead to a worse outcome. And it quickly figures out that the place to be is somewhere between these 2 potential leaks. But in this case, I put a hard constraint of only one well, so we start to see a trade-off curve like this that's telling us basically that one borehole can't effectively monitor both of these leaks very well. So from there, we can give the user the information to decide which of these 2 conflicting objectives of theirs is really the priority, or they can try just loosening up their objectives and running it for more iterations. Then in this example, we're designing a gravity survey to monitor both of these 2 leak locations. We start a random survey geometry and we make a series of small changes to it until it's able to make a reasonable trade-off between, and now there are 3 objectives. So we want to minimize the time to detection for both of the leaks and also minimize the cost. And so you can see eventually there's no real trade-off between time to detection, but there is some trade-off with the monitoring cost. So a smaller geophysical survey can be cheaper and still detect either leak reasonably early, or a larger survey will be more expensive, but it will detect both leaks as early as possible. And so we end up producing sort of a heat map telling the geophysical survey team the best place to go. Now, this more detailed example starts to show the 3D nature of the problem. So we don't just need to know where to drill in order to get the sensors to where we need them. We also need to know how deep to drill. And so at iteration 0, these red lines are our randomly proposed well locations, and then the red dots indicate the sensor packages installed in them. And the blue lines connecting them represents the sensitivity kernel between two sensors. So if we're doing cross-board geophysics, then that pair of sensors would be able to detect a contaminant plume if it intersects any of those volumes. And so at each iteration, sometimes it modifies the surface geometry of the geophysical survey at the surface, and then sometimes it modifies the location or depth of a well. And we look at which leaks we are and are not able to detect with each configuration, and we accept or reject each proposed change based on that. And so we're still fine-tuning the algorithm itself, but it does start to come up with some interesting trade-off relationships that could help us zero in on an optimal strategy for a realistic site. And so DREAM was designed with carbon sequestration problems in mind, but it could be used for a variety of different subsurface monitoring design problems. And since it doesn't handle any of the forward modeling, it's something that you can use to post-process an ensemble of simulations using a pretty modest laptop or desktop machine, not a supercomputer. And we're hoping it will start to see some adoption in industry and help facilitate conversations about risk and uncertainty between regulators and site operators and the general public. And again, it's been released on EDX, and you can access it at this URL. It has a lot of the features described here, but some of them are currently under development as part of DREAM version 3.0, should be released next summer. But if anyone is interested in beta testing an earlier release, then please contact me here. Thank you for your time.
Hello everyone, I'm Lianjie Huang from Los Alamos National Lab. I'm going to talk about the NRAP tool on optimal design of a microseismic monitoring network. Cost-effective long-term microseismic monitoring is crucial to ensure safe geologic carbon storage. This NRAP tool is for optimal design of a microseismic monitoring network using surface seismic station in all borehole geophones for cost-effective microseismic monitoring at geologic carbon storage sites. The tool can be run on Linux, Windows, and Mac OS. The GUI is based on Java, and this is the command line to run the tool. The first window it pop up is this one. You click OK button, and then will pop up this window. If you need a user menu, you can click on this button, and will pop up a window to show the user menu is a PDF file. When you click this button, and will show a few action items you can do. For example, to plot the result, to save the parameter, to run the tool, etc. So the first step to run the tool is enter the parameter by clicking this button. You need to provide a velocity model, define the geophone distribution area, define the target monitoring region. You can also change the number of a CPU core to be used to run the tool. The default is 1 here. You can return to the main page to start over by clicking this button. After you enter all of the parameters, you can save the parameter and run the tool. The first step is to provide a velocity model. The model size should be fewer than about 1 million grid points. There is a different way to provide velocity model, including 1D value, 1D velocity model, and 3D velocity model. So the first option is to manually input a 1D model by clicking this option. You can enter the number of layers and then click Apply. Here is an example of a 3-layer models. You enter 3 here and click Apply. It will pop up this panel. So you should define the layer thickness of each layer and then define P and SOA velocity value in each layer. The other two methods to provide a velocity model is using a file, so including 1D velocity model file and 3D velocity model file as shown here. Next step is to define the geophone distribution area. You click this button and you can see that you can define surface geophone, borehole geophone, or you can define manually based on the geophone distribution you want. Next step is to define the target monitoring region. You define a region within the model in here. After you enter all these parameters, you save the parameter by clicking this button and then run the tool by clicking this button. And then a progress bar as shown here will show the job progress. When the job is done, the result is automatically plotted. If you want to plot manually, you can just click this button to plot the result again. And here is the result of the 3-layer model I entered earlier. And this is the standard deviation error of the event location. And this is the total number of geophones. As shown in this figure, you can see that 8 seismic stations are needed for cost-effective microseismic monitoring, because if you increase the number of seismic stations, it doesn't significantly reduce the event location error. We use this tool to design microseismic monitoring network at Farnsworth CO2 EOR field in Texas. And again, this is the number of seismic stations, and this is the standard deviation error of event location. And this figure indicates that 16 geophones are needed for cost-effective microseismic monitoring at the Farnsworth CO2 EOR field. In summary, we have developed an NRAP tool for optimal design of a microseismic monitoring network for cost-effective microseismic monitoring at geology carbon storage sites. The tool will be released soon pending on NETL and NANA's approval. And thank you for your attention.